Hello, I'm Giovanni Toffol, a postdoctoral researcher here at the Department of Geosciences of the University of Padua. And today I would like to present you my most recent publication that is published on the journal Science Advances. This research was part of my PhD thesis and was conducted together with Giorgio Pennacchioni from Padua and Luca Menegon from the University of Oslo, David Wallis from the University of Cambridge, and Manuel Faccenda again from Padua, and Alfredo Camacho from the University of Manitoba, and Michael Bestman from the University of Vienna. The main goal of this research was to quantify the energy dissipated on fault during an earthquake, and this estimate is fundamental to understand the mechanics of earthquake faulting and earthquake rupture propagation. We know that only a small amount of energy of the entire energy released by an earthquake is dissipated as seismic waves, which are the waves responsible for the effects that we can see on the surface, while most of the energy is dissipated along the fault. And there are different processes that can dissipate this energy. The main energy sink is the heat, so the frictional heating, the energy that is dissipated during the earthquake slip, and it is transformed into heat. Another energy sink is the fracture energy, the fracture surface energy, and it consists of the energy that is consumed to produce new surfaces and to propagate the seismic rupture. And then there is also another small energy sink, which is the crystal plastic energy, and it consists in the energy that is used to strain the crystal lattice of the fault rock minerals around the propagating seismic rupture. So this last energy sink was never estimated before, and with this study we wanted to estimate this particular energy sink and to compare it with the other two main energy sinks that I mentioned before, the surface fracture energy and the heat, to provide a complete budget of the energy dissipated on fault during an earthquake. The earthquake energy partitioning has been estimated with various approaches, mainly from the study of seismic waves or from numerical modeling, and also in the lab, reproducing small earthquakes at the lab scale. There is also another approach, which is the study of exhumed fault rocks that recorded earthquakes in the past. And in particular for this research, we followed this last approach, studying an exhumed fault rock bearing a pseudotachylyte, like you can see here. A pseudotachylyte is a quenched frictional melt that is produced during seismic slip and is considered as an evidence for earthquake rupture. It can be considered as a fossilized earthquake. So we collected a sample, a rock, a piece of rock with a pseudotachylyte from Central Australia, from the Musgrave ranges. The sample was collected along the Woodroffe Thrust in the area of Mount Fraser. We collected this sample that recorded a single earthquake, and we studied it with the advanced electron microscopy technique with the help of a scanning electron microscope. So from the sample we cut a thin section, and the main part of the studies were performed in Oslo, where I was doing a visiting period. I was spending there 6 months, and during this period I collected some HREBSD maps. HREBSD, high angular resolution electron backscatter diffraction, is a material science technique that has been recently applied also to geological materials. And with this technique, we studied some big garnets that were crosscut by a pseudotachylyte, so that were shocked by a seismic event. And with this technique, we were able to measure with extremely high precision and high spatial resolution below the micrometer scale. We measured the rotations and the elastic strains of the crystal lattice of the garnet. And from these rotations and elastic strains, we calculated the density of these locations. These locations are punctual defects inside the crystal lattice, and the residual stresses that were still retained inside the lattice. And from these locations and from the residual stresses, we were able to calculate the crystal plastic energy that was dissipated during the propagation of the rupture. And we obtained a value of 40 kilojoule per square meter. Then we calculated the surface fracture energy, and to do so we focused our attention on a pulverized domain along the pseudotachylyte fault vein. Basically, during the propagation of the rupture, we have this production of surface by fracturing and pulverization in the host rock minerals. So we selected a domain with the garnet that was pulverized with a cluster size that was down to 20 nanometers. And by measuring the cluster size distribution, we were able to quantify the energy required to produce all those fractures. And we obtained a value of 0.5 megajoule per square meter. And lastly, we calculated the heat by considering the thickness of the pseudotachylyte vein and its mineral composition, and assuming a maximum temperature of 1350 degrees Celsius. And we estimated a value of 13 megajoule per square meter. So as we can see, the heat is the main energy sink that accounts for most of the energy dissipated along the fault plane, and the surface fracture energy and the crystal plastic energy are smaller quantity compared to the heat. What is important is that in this study we were able to quantify all these three energy sinks to show that there is a clear hierarchy in the distribution of the energy. And we also show that rocks can still preserve all the effects of a seismic event, of the propagation of the earthquake rupture and the slip. And we as geologists, we can collect rocks that recorded seismic events, and we can study them, we can infer all the processes, and this observation can help us to understand the mechanics of earthquake and how seismic rupture propagate at depth.